is the name of instructor? Instructor is us, right?
No.
What's them?
Whenever you are.
Today we're going to go over the basics of axial stress and strain. I made a Bakst. I made first year at Drexel, and I did my undergrad at college graduated in mechanical engineering. So, stress and strain, what is working here? Anyway.
Stress is the quality of the material that tells you how much force is in that given section of material based on the size.
Okay. So putting that into more unit words.
You could say it's a force over area.
Okay, yeah. And then strain. Has anyone seen this word before?
Change in dimension versus the original dimension.
Yeah.
Usually put in terms of length, but not necessarily.
Okay. But in this case, we're talking about axial stress and strain. So it's all exactly right. And this is represented by the Greek letter epsilon, and this is represented by the Greek letter sigma, both. Now, we usually look at these kinds of things in more complicated scenarios. But let's look at simple scenarios now. Let's say we have a bar, and the bar has a rectangular cross-section of 1 centimeter by 1 centimeter. And the length here is 1 meter. And we're going to apply an axial force in the direction of the bar of 100 meters. So now, since we're looking for the stress, and that's force per unit area, which area is this force acting on? Anyone see it?
Say it's on 1 centimeter by 1 centimeter cross.
Yeah, this one, the cross-sectional area, because that's right here. So the force is 100 newtons over the cross-sectional area, which is 10 to the negative 4 meters squared. And that gives us 1 million newtons per meter squared, also known as pascals. Does everyone follow? Cool. So now, we didn't say anything about what material this is. Let's say this material is steel. And the property that relates, the equation that relates stress to strain is here. Where this large E, this uppercase E, is known as the Young's modulus, or modulus of elasticity. And what happened was, to identify this material, people did a string of experiments and found that when they plotted the stress against the strain in the experiment, they found that it reacted something like this. No die. And this would be fractal. But here, along this region, it was rather linear. And this is for most all isotropic. And this slope right here is the Young's modulus. So, relating those, knowing that this is steel, where the Young's modulus is 200 gigapascals, we can easily find the strain. Where the strain is does anyone know what the top of the head of it? It's a very small. One 200, so 0.0005. 5,000. The strain is 5,000. And so that is the strain of that simple bar.
How much time?
Yeah.
Another minute.
Another minute? Okay. Now let's say you have a composite bar. Where these two are glued together really, really well. And this still has its 1 centimeter by 1 centimeter. And this, say, has 2 centimeters by 2 centimeters. And now we're going to have the same 100 Newton force. So now, since this isn't moving, statically speaking, the force has to transfer between this and this, right? Everyone follow that? So, that means that if you were to look at just this piece of the bar, there's also a 100 Newton force acting on it. For all intents and purposes, this bar sees 100 newtons. So we already know that the stress in this section is 100 megapascals. But now we have the same force, 100 newtons, over a different area. So do you think that the stress will be larger or smaller for this section of the bar? Right. That makes sense to us, because the bar is bigger, and thus should be able to hold more. And so this stress is 4 times smaller than this. There you have it. There's stress and strain, axially. Very good. So next week, we'll go over composite materials when the bar is made out of